Alright, go over this real quick. Just to make sure we all got a handle on this. We have a feeder that's feeding two motors. We have a feeder that's feeding two motors. Over here I have overcurrent protection. I already drew that one. Okay, so code says we have a feeder, but we have to have means to protect each motor. So we have to have short circuit protection, ground fault protection at each individual motor. This is a feeder. The only thing we're concerned when we're doing the feeders and all these motors come in is to find the main breaker and the wires. The main breaker and the wire. Okay, once we get down to the motor, from here down, it's an individual motor. From here down is an individual motor. I didn't explain that last time. I just was hoping that seeing the picture that you would understand that now from here down, it's that single motor and that's it. So my protection here and my overloads here is that single motor. This one has nothing to do with this, and this one here has nothing to do from here down with that. Only with our main wire and our short circuit ground fault protection. It's not called an overload. It's not called a overcurrent protection because it's not against overcurrent. It's against short circuit and ground faults. Because our overloads, our overcurrent protection is right here in our overloads. Because this is going to be sized to protect that motor. These are going to be sized to protect that motor. So again, I went to, because this is a three-phase, I'm at 208, three-phase, so I went to table 43250. I had it down here, 43250. For the 2 horsepower, it was 7.5. Okay, we're using a breaker multiplied by 250%, give me the 18.75. Okay, next breaker size from there is a 20. So I made it a 20 and then added all other motors. Okay, so I added that second motor, 4.6, so it's 24.6. Code says this because I already went up here, I can't go up here. So that means I have to go back down, so my breaker would be a 20 amp breaker. For my wire, again, use my largest motor, which is a 2 horsepower, 7.5, where's it, right here, 7.5 times 125%, gives me 9.375. At the other motor, which is this one here, 4.6, not down here, but over here, add it, and that's 13.975, 14 amps, that's a 14 gauge wire. Building, when we're wiring motors, okay, smallest building wire is 14. Okay, you can use smaller wires if you're doing your protection and everything else. You know, if I had it from here to here, guess what? I could use a 16 gauge. I could use an 18 gauge because these overloads are protecting this wire so it doesn't get more than what the capacitors are. That's a different story. Wait till you get out in the field and you can learn that. For now, we're just taking the normal wire size that we need. Code says smallest building wire is a 14 gauge. That's where we're going to stay at. Alright? So now it comes up here. So I need a 14 gauge wire. 14 gauge at 75 degrees C. It can handle. Okay? Before we talked about, oh well, we don't know what our terminations are. Are they 60 or 75? So a lot of people have a tendency to look at that 60. For most parts in today's world, we can use a 90 degrees C. I mean 75 degrees C. Always remember, it's 100 amps or less. We go to that 60 degrees C. More than 100 amps, we go to the 75 degree. But on today's world, out there on the outside, 75 degrees C on everything's okay. Unless you already know it's going to be 60 degree. Okay? Now when we go to find this breaker here, if we want to find this, okay, so I would get that 7.5, say these are time delay fuses. And that'd be multiplied by 175%. So 7.5 times 175%, 13.125 amps. So that would be, here would be a 15 amp fuse. different color. And then over here, again, times 175%. 8.05, 15 amp fuse. Okay, we do our overloads. Okay, our service factor, I didn't give you a service, well here it is. 1.15, 1.15, that's why I gave you the service factor so you could find the overloads. So again, now we're going to use the nameplate. So 5.7 times 125%. Okay, 3.8 times 175%, 125%. I'm sorry. .75 amps. .125 amps. Okay, on the overloads. Don't round up, don't round down, because they come in fractions. So they always have, like, it might go, let's say it goes from 6.9 to 7.14. So now we know where we're at, you know, and then it goes from 7.5 to 7.83. So they come in fractions. So when you get the overloads, always leave whatever pops up in the calendar. Always leave what pops up in the calendar. One of the questions, it says SF 32.2. I think it was question number 4. Max. So SF 32.2 max. That came off a motor. That is an actual nameplate. And that quiz that I sent that was due last night, those are actual nameplates. I just went in, I found that. Okay, what does that mean? It says that your overload, maximum overload is 32.2. Okay, your maximum overload is 32.2. So I hope this covers a little bit better, and I hope it makes it a little makes it easier to understand. Okay, again, have questions, ask. You're not going to learn and you're going to get stuck if you don't ask questions. You send me an email, I'll answer it, you know. Alright, now we get to power factors. The power factor, because the current is lagging the voltage, there's a dip in your thing. So when you have a motor, especially with motors, when you have a power factor is, you know, when we get, here I'll use an example. I got 120 volt motor, and then it's 3 amps. Just as an example. Okay, what's the wattage on it? P equals I times E pi. So 120 times 3. P equals 360 watts. Okay, that's our power. That's at 100%. Okay, that's at 100%. Sometimes we're not at 100%. And the reason they want to, a lot of times they want to clear this out, is to make sure we can get in. In our residential book, it covered a little bit better. Residential book talked about taking a reading with your watt meter, and then taking an amp reading. So you get the actual wattage and the actual amperage, and multiply it by the applied voltage. So let's say using this is simple math looking at a nameplate. This is simple math looking at a nameplate. I go in there and I read, and instead of having 120 volts, I have 118 volts. Okay? And I get my clamp on, and instead of having 3 amps, I have 2.8. This is an example. Okay? The problem is where the utilities come in. If I do that math now, let me go here real quick. 118 times 2.8 equals 330.4 watts. So now the problem is, this is my true power, and then I have my apparent power. So one is one, and then the other is what's there. Okay, so now I want to go, and the formula is power factor. Talking about there, power factor equals true power divided by the apparent power. .4 divided by 360. Power factor equals 0.92. Okay, so that's 92%. So this is 92% efficient. This is 92% efficient. So this is what we're talking about. They're using the cosine and the phase angle. The cosine is 0.866. So if you put this in one and this in the other, your difference is going to be 86% efficient, 86.6% efficient, like it shows it in the book. But this is why. The problem is, and the utilities don't like this, and this is why we have to correct it. It's more of the motors, is because they have to provide this. Okay, they're providing this, but you're only using this. So this is what you're paying for, and this is what the utility's providing. So the utility has to make the 360 watts available so you can use, so you can pay for 330. Okay, I'm talking about one load. You get an area that has multiple loads, and this will add up. All of a sudden, they're producing more electricity than what you're using for you to pay, because that power has to be available. That power has to be available. If this went up to 100%, well, this has to be available. So if this changed and it went up to 100%, this has to be available for this to work. Okay, so the utility is producing more, so you can use less and pay for less. So they're losing money. So that's why power factor is an important part. Oops, wrong way. So power factor is a ratio of the true power to apparent power. Power factor is true power divided by apparent power. Okay, the apparent power is, take a nameplate for a reading. You multiply the nameplate times the voltage. Okay, and then you divide the other. And then you take an amp reading, and your amp reading say something different. Okay, again, this is what it's showing. So I took a voltage reading, and I took an amp reading, and I had 118 volts, and I had 2.8 amps. Okay? When it should be here, and this is at 100%. Well, I'm not at 100%. I'm at 92%. Unity is when true power and apparent power are equal. So, in a perfect world, we want everything to be equal, but we don't have a perfect world. Electricity isn't perfect, so that's. But you can correct this. This can be corrected. Power factor improvement. Low power factor is improved by adding capacitors to the circuit, reducing the lag between the current and the voltage. Capacitance reactance contracts the let me get my. So it says, ideally motor circuits would have a power factor of 1, however this realistically unattainable. Low power factors can be improved by adding capacitance. This introduces capacitance reactance when the counter reacts to inductive reactance and improves the power factor. A lot of times you can find the power factor on a motor, and you look at the motor and it says 0.86 or it says 86.6%. That's that cos sign. Okay, so that power factor is already low. Motors aren't 100% efficient. Some already come with a capacitor on it too. Clean that up a bit, and some don't. This says motor nameplate. This says capacitors are rated for their reactive power normally in units of reactive kilovolts. Motor manufacturers provide charts that can be used to determine the capacitor size needed to change the power factor of the motor. And that's 13.3. They don't have it on here. No, they don't. And it says see figure 13.13. To use a chart, first locate the existing power factor to the far left column, then desired power factor. And multiply the number at the intersection of these numbers by the true power of the motor in kVA to determine the capacitor reactance in kVR. So it says, so I'm on page 198. And I'm at 92%. Go to the left. Existing, I go to 92. Let's say I want to take it up to 100. So it's 0.392. 0.392. It says a sample problem says a 55 horsepower three-phase motor full load current of 65 amps at 460 volts, a power factor 65%. What size capacitance is needed to raise the power factor to 90%? So I'm going to get the, let me write it on here. So it's, yeah, the true power, I'm sorry. True power equals I times E times square root of 3 times power factor. So true power equals 65 amps times 460 volts times 1.732 times 65.65. That's 65%, 0.65. So true power equals 33,661 for 33.6, 33.7 kVA. It says determine the number from the chart. The multiplier for the intersection at the existing 0.65 power factor and desired is 90. Power factor is 0.685. So I'm going to multiply this times, and then I'll do it up above. 685 equals 23.1 kVR. kVAR. I'm sorry. Kilovolt amp. So a capacitor rated at 23.1 kVR can be used to correct the power factor. Now let's go to the one up on top. Okay. Define true power. So mine is true power. It's 2.8 times 118 times 0.92. I don't have to add the square root of 3 because I got 120 volts. Okay. 0.8 times 118 times 0.92 is okay. So this would be 0.304 kVA. I want to get to 100%. So I'm at 92. Multiply this by 0.426. So that equals 0.129 kVAR. Okay, so we need to find our reactance to correct the capacitor, correct it up to 100%. Okay, so it's using the table. Look on the left, where are you? Then go across, and that is your multiplier. Your multiplier, you're going to multiply it by your kVA. Okay, this is my VA. Down here it says K because I knocked it from 33,601. I rounded off. Same thing over here. Because it's less than 1,000. That's why the decimal points here. That's less than 1,000. That covers chapter 13. There's no assignments with this one. This pretty much covers it. Again, when you have motors, let me go back. Okay, any questions on that, you can let me know. We have motors, okay, and I didn't add it now, but I'll talk about it. I didn't want to confuse everybody. So remember is, now let's say I have, a 400 watt, 800 watt, I'm just going to say 800 watt load. Okay, this 800 watts, I would add it here. Okay, so if I get 800, so let's say I'm adding an 800 watt load. 800 divided by 208 divided by 1.732 equals 2.2 amps. Okay, so I will add it here. 2.22. So this would be 286. So 26.8. Now I got a 25 amp breaker. Now I got a 25 amp breaker because this 800 watt load took it above 25. I'm at 26.82. So that's adding other loads. In the answers, I forgot, I just got the 480 volts. I made it where I could do it simple in my head, just so you got the idea. Again, it's just trying to get everything. I know it's hard. I know it's hard. You trying to learn at home and not me being up front where you ask me questions like when we're in the classroom. Again, I'll try to be more explainative. Explain the stuff a little bit better, and hopefully we get it all taken care of, get it all under thing. If we get done early enough, we'll come back and we'll go over what needs. Okay, on these motors, for those that were in my Electrician 2 class, remember we covered this real good. We covered this real good in Electrician 2. So we covered this real good in Electrician 2. So again, I try to give it to you. And the reason we keep going over and over and over again, you know, we did electrician 1, electrician 2, and then a lot of the stuff that we're doing now is similar to electrician 2, but a little bit different. It's similar, like we talked about power factor in electrician 2. We talked about power factor. And we take the watt meter and take the amp meter. And that's it. You know, we didn't have to worry about adding capacitors, so they added capacitors. When you get into electrician 4, they bring this up again, this power factor. There's a little bit different. If y'all were taking it with me, that power factor, we will be talking about building an industrial plant, the engineering part of an industrial plant. So that one's got a lot of trig. Yeah, drives my head crazy sometimes, but yeah, but I got it. Yeah, I did it in high school. I did it in college. I did it in high school. I did it in college. Hell, that was 40 years ago when I did that. When I taught electrician 4 for the first time. Whew, it was hard, but I got it all under control. So again, this would be covered again. But now we have to find what the power factor is, and then how do we correct it. And I'm not talking about correcting one little motor. We're talking about correcting a power plant, an industrial plant with metal lathes and saws and drills and everything else. So power factor is a problem because utilities, you know, some areas utilities where your power factor is under 90% or whatever it may be, and then they say you pay a fine. The fine is you pay higher electricity. They have transformers that are reading on your CTs. So they have a auto transformer and a capacitance transformer. And then what happens is when your power factor drops, because there's 2 meters. One meter reads your when your power factor is above a certain percent, and the other one reads is when it drops below. So as long as I stay at 90% above, I may be paying 20 cents a kilowatt, 18 cents a kilowatt, whatever it is now, whatever they pay. But if it drops below 90%, guess what? Per kilowatt can double the price. Utilities don't want to pay double the electricity when there's a way to correct it, so they don't have to pay that. So the engineer or the electrician that's doing it, it's their job to make sure to maintain that power factor above 90%. Why? So they don't get, but it also creates problems with motors. Okay, if your voltage starts dirty, if you start getting a lot of dirty power, it affects with electronics and everything else. Okay, that's a different chapter. There's more on it in the industrial where we start talking about harmonics and everything else. That's in the industrial book. We don't have it in this book. We'll get into it in another class. All right, y'all have a good one, and I hope I was more clear this time. And good luck on the test. Test is going out with this email. All right.